Hi everyone, welcome to today's Software-Defined Networking web seminar series by Global Technology Resources Incorporated, GTRI. My name is Scott Hogue. I'm CTO for GTRI. I've been a longtime network engineer, security practitioner. Over the past, I'd say several years, I've learned a bit about SDN, and many of you who may know me know that security is very much top of mind for me. I always think as we're learning a new technology, whether it be software-defined networking or IPv6 or cloud, we need to think about, what are the things we need to consider in the design and the architecture and planning for it to be secure right from the get-go, and anticipate what attackers could do and maybe try and head them off at the pass. And then think about what are some of the cool new things we could do to enable our businesses and leverage the technology for, really positive business outcomes. So this is a web seminar in a series of 6 web seminars that we're doing this year on software-defined networking. We've had ones in the past on just introductory to software-defined networking. We've had ones on specific vendors' products, and this one is a multi-vendor presentation just focused on the topic of security, and we'll have future SDN web seminars as well. So today's talk will focus on kind of a brief review of software-defined networking. We don't want to spend too much time on that. We're assuming that you've attended maybe one of our other software-defined networking seminars. We did one a few months ago, Introduction to Software-Defined Networking. You can find that on our website if you're interested in going back and looking at that information. But this presentation assumes that you know a little bit about software-defined networking, but it's not a prerequisite. We kind of go over this concept of two sides of the same coin, like these two different ideas in this presentation. One, heads being, what do we need to think about in terms of securing a software-defined implementation? What could attackers do to attack a software-defined network infrastructure system, whether it be on-premise, in your data center, in the cloud, in a multi-tenant data center, what have you? What do we need to think about and to secure it right from the get-go? And then the tail side of today's presentation will be the other side of it is, well, now that we have a software-defined network infrastructure, what kinds of cool and interesting security things could we do with it? How could we leverage that software-defined network infrastructure to help us secure our traffic or do things in innovative ways that we couldn't achieve easily before with a traditional, IP routed network infrastructure? And then we'll have some open discussion, time permitting, time for questions and answers. During today's presentation, I'll be monitoring the chat session. If you have questions, go ahead and put them in the chat, and I'll see if I can answer them along the way, or I may wait until the end after I get through the presentation material to answer your questions. But and definitely this presentation will be recorded, so you'll be able to watch a replay of it, and we'll be providing attendees the presentation digitally, electronic, for your reference, so you have it for future reference. So with that, we'll go ahead and get started. So kind of briefly here, kind of redefining software-defined networking. This is the dictionary definition of software-defined networking. It's an approach for networking that separates control and management plane from the data plane, separating control and data and management that have typically been all in a single network device, separating out some of those functions, allowing a higher order system, a controller, if you will, be able to push configurations and synchronize configurations among multiple devices, or allow for a more complex global view of the network and allow the network to be more dynamic. Today, most networks use dynamic routing protocols to share reachability information with each router, and they build a topology, but they each only have a view of the topology from their own particular knothole, and each network element doesn't have a complete global view of everything that's going on in the network, and those routing protocols don't take into account load. of the network, or what kinds of application traffic are traversing, or how does the business rules change how traffic should be handled, and they often compute a single best path to forward traffic. There may be an alternate path that's completely unused that would actually end up yielding better end user response. And so could we separate these functions, pull them apart, disaggregate, the switching and forwarding from the network intelligence, and allow for more creative ways of doing networking? So software-defined networking is this new paradigm for network virtualization that supports our goals for application, server, system virtualization. And when we talk about virtualization, it's virtualizing and removing the construct of geography and topology from systems, and virtualizing systems, whether it be in a data center, virtualizing it across multiple data centers, or extending networks out to a cloud. So in a traditional enterprise network, you may use virtualization at the services layer. At applications, you may containerize applications and virtualize the network supporting those containerized applications. And those containerized applications could exist in your traditional data center, in a hybrid cloud environment, or in a public cloud infrastructure. And so software-defined networking is this concept of networking and virtualizing networking and changing the way we program or control networks and create policies. And the traditional SDN high-level architecture, there's a controller layer in the middle here that is where the intelligence lies. And there's a southbound protocol that's used from the controller to push configuration or push intent or push information down to the network elements on what they should do. And the network elements then are less intelligent, more commodity devices that do what they're told. There's no real intelligence in the network element. The intelligence is now centralized in the controller that has a global view of the network. And then northbound of that controller are APIs and programmability, where applications or functions or other programmability can take place to then tell the controller what is required. What are the requirements from the network? How does the application want traffic to be handled? And so this is kind of a traditional 3 layers. We have a application layer, an SDN layer. We have a kind of a control layer where the controller lies, and then we have the data plane layer. So you see how we've separated management from control from data plane here. We've disaggregated this, and we've disaggregated the switches. And now rather than having one switch or router that does forwarding and has intelligence in it to make those decisions, now we've broken out those pieces. And so this allows, for a change in how we think about networking, and has certain kind of inherent benefits. We have greater span of control. Rather than today where we log into each network element manually to make configuration changes, now we can go to a controller, make one change, and say, this is what I want to have happen, and then that gets disseminated to all the devices in the network, making administration of a network simpler or reducing errors. We get better intelligence. We can get telemetry and get network get network information from the devices easier back to the controller, and then the controller could change based on that real-time information or near real-time information about what the network is doing, change behavior of the network, and use that information to adjust as needed to support the business and the applications. Improving application response time, where maybe the telemetry that's coming off the network indicates that there's a problem, and then the network intelligently changes itself to accommodate that, either changing quality of service settings or adjusting the amount of bandwidth or scaling network in some way. So giving our network some of those, cloud properties of scalability, elasticity, and multi-tenancy. We can do rapid deployment of applications and change applications, and virtualizing the network lets us use software to instantiate new networks, new systems, new applications that ride on top of that. So have greater DevOps type continuous integration, continuous deployment of environments faster by making the network more adaptable and easier to configure quickly to support changes in applications. Like I said, simplified automation rather than logging into every device in the network topology to make a change for quality of service settings that tend to be static. Now let's make those quality of service settings defined based on a policy and push down to network devices as network traffic patterns change and adapt, and not having to do that manually to hundreds and hundreds of network elements. So it gives us this opportunity to open up the network, open up from traditional vendors that might have had everything in one system. Now we can have disaggregation and might give better economies of scale, better, better for the consumer to be able to pick and choose what they want, and better reduction of costs, and the ability to use commodity hardware for the underlying network elements. So common SDN use cases are like the components of a submarine, segmenting or creating zones or enclaves within an environment, creating different portions of a network, network segmentation, network separation, so creating either for multi-tenancy in a cloud environment, or just separating, engineering from marketing, from sales, from HR, and segmenting groups based on their function and putting applications in those functions. Over here in the upper right, the fish problem, we may compute the yellow path as the least cost path with our IP routing protocols, and that's the path that all traffic takes regardless of any changes in traffic patterns. When the yellow path gets full, traditional routers won't realize that there's this alternate green path that's completely unused that could in the end have greater, end user performance, and giving intelligence to like router 2 and router 4 in that diagram to be able to say, hey, let's use this alternate path and improve application performance. In the lower left, spine leaf architectures, having this data center fabric. You build out these data center networks to support big data applications. There's lots of top-of-rack switches, lots of spine switches, and you don't want to have to program each one of these devices manually. You want to be able to create one policy and push it down into all the elements. And so easing automation, improving consistency, reducing human error. Down here in the lower right, in the past we've created, filters or lists or policies that have been if, then, else, top-down, first match, action takes place kind of policies. And what we want to do is we want to be able to route packets or change the way we do things, maybe based on Boolean logic. This kind of packet from this host and this time of day, but not this time of day, I want to have this behavior take place. I want to have none of this type of traffic, but all of this type of traffic from these systems to these, destinations, and treat them this particular way. So we may want to use Boolean logic and have more flexibility in how we build policies. Software-defined networking can support those use cases. Additional use cases, maybe we want to, take a page from the DevOps teams and use some automation tools, and use automated service delivery to support our CI/CD, DevOps goals. And, when in the past, when these groups have functioned and they needed to add a new system to an Ethernet port and put that system into a VLAN, they had to issue a trouble ticket and have the network engineer then log in manually to make a change to the Ethernet switch. If we can have programmability, then these folks can just integrate into those APIs of the existing network switches to make the change dynamically as needed, and reduce a human having to do something manually and improve the speed of deployment. Or maybe we want to handle packets in different ways and we want to copy them and send them to a network packet analysis, a network packet broker, or do tap aggregation or something like that. Or we just need applications and different types of systems to talk to the cloud, and we want network function virtualization, and we want to virtualize load balancing and firewalling and switching, and extend that to a cloud environment. Some of the common use cases of software-defined networking. So to talk about the security of SDN systems, what can we expect, are the security sticking points? What can we anticipate an attacker doing to an SDN system to leverage gaining access or disrupt a system? We can think about what are typical attackers' motivations to disrupt or infiltrate IT system of an enterprise environment or a multi-tenant data center. We see that more common SDN security concerns are attacks targeting the controller. You can see that the controller is where the intelligence is, and if the attacker could disrupt the controller, then that affects traffic forwarding in the network. Or would the attacker want to instantiate new flows into that controller and create their own forwarding? Spoofing traffic to the northbound API to the controller could get the attacker to have the network handle traffic the way they want to. What if the attacker were to create their own controller, a rogue controller, and then get the network elements to believe it is the source of record for the policies on how traffic should be sent across the network? That would be an issue. Or how could the attacker then target the network elements by spoofing southbound protocol messages to them to instantiate flows? Or could the attacker attack these data center interconnect protocols that generally don't have any form of authentication or encryption or security in any way? Could they target these transport protocols or overlay networks? Could the attacker, target the underlay or the overlay network to achieve their goals? Here's kind of a picture that shows graphically what I just described. The attacker could be over here, trying to attack a network element. The attacker could be in the middle of this traffic, of the southbound traffic from the controller, changing and modifying the commands and how the network element is forwarding. Could the attacker be eavesdropping in traffic? Could they change network traffic paths to send it through a point where the attacker is eavesdropping? Could the attacker set up a rogue controller, could create a DOS condition for a network element or the controller itself? We can think about where could an attacker be. Now, we want to make sure that attackers haven't compromised any systems in our SDN topology so that they could have the ability to send these kind of messages. We want to prevent against unauthorized access, but we can think about, well, what might an attacker do and how would we then secure a SDN system to make sure it was impervious to these attacks right from the get-go. So there has been research done on SDN vulnerabilities. Graduate students at the Korea Advanced Institute for Science and Technology in South Korea, Daejeon, their network and system security laboratory has gone through a process of creating this vulnerability genome project where they've kind of highlighted all of these different vulnerabilities to an SDN system and categorized them in different ways. They've classified SDN misuse attack, control plane specific attacks, data plane specific attacks, and you could read their research on sdnsecurity.org. There's also been a lot of work done by Dr. Sandra Scott Hayward from Queen's University in Belfast, where she's done research on the same types of, looking at what types of attacks can be common. And so you can read their research that's available online. So we've also seen that, there have been vendors that have had to publish, vulnerabilities and patches due to, security researchers or attacks on their SDN systems. Some SDN systems may rely on open source software that has then discovered vulnerabilities in it. And those vendors have had to publish updates to their software that has to be pushed. So like anything with regards to security, we have to keep our software patched. We have to keep our SDN software patched because now it's a software-defined network. So we're probably going to, in a software-defined networking environment, be patching our software on the network elements more frequently than maybe we do today, where we let our Ethernet switches run the same version of software that they ran the first day when they were installed. You know, if there are SDN systems that have vulnerabilities in Bash, OpenSSH, OpenSSL, network time protocol, you know, there have been vulnerabilities published with those protocols, and SDN vendors have had to, in response, publish, you know, improvements to those vulnerabilities in their products. And there have been several, you know, public documented vulnerabilities in Open Daylight and security advisories in the Open Daylight group. And initially, the Open Daylight group didn't have an SDN security-specific group, but now they've formed within Open Daylight project group and folks that are focused on security and proactively handling security in the Open Daylight controller. There was a net dump vulnerability that took many months to correct, and as a result now, Open Daylight has had increased focus on security. Open Network Install Environment, ONE, if you're not familiar with it, is a way that SDN switches can be booted up online, be configured and cabled, be booted up, and then get their configuration from a controller and get their operating system and boot up and kind of bootstrap themselves onto a network. And there's been vulnerabilities with the Open Network Install Environment on switches and different controllers. Cumulus networks, privilege escalation, Cisco APIC, root access vulnerability. You know, these have been patched and addressed, but you can see from publicly announced, you know, vulnerabilities in software-defined networking systems what attackers or security researchers may be thinking about, and they're along the lines of what we just talked about. So how do we harden our SDN systems, or how do we anticipate, based on, you know, what we can anticipate from an attacker, what security research has been done on SDN systems? You know, now we should think about, as we start to roll out SDN systems, we want to make sure they're secure right from the get-go. And so, you know, we want to use secure protocols for southbound communication between the controller and the network elements. We want to make sure that any northbound protocol that's being used on the controller is secure as well. So we want to use TLS. We want to authenticate the controller to the network devices so the network devices don't start believing flows from a rogue controller. We want to have a high availability controller, so if there is a denial of service or a failure in one of our controllers, it doesn't completely, you know, prevent our ability to forward traffic across the network. So we want to have multiple controllers share a database of policies and synchronize those policies between themselves, for greater high availability there. We want to prevent unauthorized access to the SDN systems, like I said before, keeping attackers off the network, keeping our systems patched, keeping malware off of our systems so that an attacker couldn't remotely control a system that's connected to the SDN network. Those are all best practices we would want to follow. We could use an out-of-band management system for that control protocol for talking to the northbound control, build a separate overlay network or a slice of our network and put the northbound communication in that enclave to prevent anybody else in the network or a system or a server being compromised from being able to communicate to that northbound API. We can separate that traffic. That's a practice that's done in some SDN vendors' solutions. We could harden the controller itself. Many times the controller may just run on an open source Linux-based operating system, and it's not hardened in any way. So you have to harden it just like you would harden a typical host on your network, and only allow it to have the minimum level of functionality that it needs to be functional. We want to monitor the controllers for suspicious activity, look for flows, look for things that may not be what we intend. We want to use secure coding practices when we're writing the software that is controlling our network and assess that. I've seen many SDN controllers go into production with default passwords. You know, admin is the default password for some SDN controllers, and username, password. And if the attacker knows that, they could easily then start to control the network. And we want to use data center interconnect protocols appropriately to, you know, and use them securely. validate flows and network devices against controller policy. And now that this is software, we can have it check itself. We can say, I've told you what the policy I want in the network, and now tell me if there's anything being done that doesn't match that policy. So you can have software checking the SDN network environment. So those are kind of things that we need to think about to harden a system, an SDN system right from the get-go. So when we think about the other side of SDN security, you know, we think about, well, what could we do with an SDN system to help create new and innovative security solutions that we have a tough time doing today with traditional network devices, with traditional middle boxes and firewalls and IPSs, you know, proxy servers, content filters. Those are the things that make up a typical enterprise perimeter, the functions that might be implemented, you know, in a data center. How would SDN change the way we build a security or change the way we implement security and make it pervasive throughout the environment? Now we're going to talk about the tail side of today's presentation, which is these 6 SDN use cases: traffic filtering, network slicing, DDoS mitigation, NAC, maybe something you forgot about for a while, NAC, security traffic monitoring, and this moving traffic target defense system. So these are just some ideas that might get your mind turning, and we'll go through some examples of implementations of each one of these to show you that these are something that could be implemented potentially in your environment. But hopefully this stimulates your creativity and you think about these things and think of some innovative and creative things you could do with SDN to make your enterprise more secure. So in the past, you know, we have really put firewalling at the internet edge, at the perimeter, and our firewalls have ended up looking like Swiss cheese with so many permit statements. Many, you know, security system administrators simply just add rules to firewalls. They never delete rules from firewalls, so it just gets punched with more and more holes. And so as a result, we've seen, you know, erosion of the security perimeter. We've seen erosions of security perimeter with the use of cloud-based systems, remote users, teleworkers, you know, and people who travel, but yet want to have that in-office experience. You know, we have not been able to create policies very easily now that say that which is not permitted is denied, but maybe we could use the SDN switch to enforce that type of a policy, where if traffic hasn't been permitted by the controller, the switch would drop certain types of packets, or maybe based on network behavior, push down a policy to all my network elements saying this is bad traffic. We just found out about this through some threat intelligence. Let's push a rule to all of our network elements saying to drop a certain kind of traffic. Today, to do that, you'd have to log into every device manually or script it in some way to push those commands out, push that policy to all your network devices. But with an SDN system, that may be easier to achieve. Cisco APIC EM can configure ACI policy for, you know, and push that out to network devices and stuff. If it's not permitted, then the traffic may be blocked or something like that. We could integrate SDN system with Cisco Identity Services Engine for device profiling, user authentication, or trust tagging, and based on that information, then allow traffic on a network. We could do traffic steering or steer traffic to a firewall to then force traffic to go through the firewall before it leaves the network. So essentially, we're making each of these network elements act like a firewall. So now every port can have that ability to have a rich security policy on it, and we can, you know, consolidate that policy in the controller and push that out. So sometimes this is also referred to as a software-defined perimeter, or you may hear that word used to define how SDN can be used as a perimeter to build this type of a policy, or you could use this type of firewalling capability in virtual switches in a data center environment. So that's one use case. Another use case may be network segmentation. We kind of mentioned that's a common use case of SDN systems is, you know, creating multi-tenancy or segmenting, creating enclaves or zones. And you've heard of the term microsegmentation, but basically, again, taking the submarine analogy, chopping up our network into different areas and into these logically separate networks. Sometimes it's referred to as network slicing or campus slicing. You create these enclaves. Today, we use virtual routing and forwarding, or VRFs, and much of that configuration has to be done manually on every device, and every device has to be synchronized and have the same VRF policy and network color applied to the routing. But this could be done easier with a centralized control plane. We can enforce strong isolation between slices, and we'll talk a little bit about flow space here, but basically saying one slice cannot affect another slice. Cisco's extensible network controller has a network slicing application. FlowVisor is a special purpose open flow controller that can create these types of these functions as well. Many SDN systems have the ability to create these logical slicing. Kind of another picture here showing an XNC creating these different slices, or you can think of a campus being sliced. I don't want the history department to talk to the engineering department, or I want to separate them. Or I have a computer science department where I want to build an overlay network where those crazy computer scientists can create the next protocol, IP version 7 or something like that, and I want them to be able to be isolated, but yet have the ability to experiment and do something innovative and interesting. So that's kind of this concept of network slicing or campus slicing. I talked about this idea of flow space, the ability to take and create almost a three-dimensional model of source address, destination address, TCP, UDP port numbers, create this space, this three-dimensional space, and then as long as each controller is functioning in a different three-dimensional volume within that space, if you can imagine that. You can't see my hands moving in my gestures, but you basically then can have different controllers monitoring different types of address space or different kinds of flow space. So let's say I want one type of controller to handle traffic going across my network for all of the 10.0.0.0/8 IPv4 addresses. Or I want to have another controller controlling the 172.16 address space. So I've used two controllers, and then I use FlowVisor to allow each of those controllers to function for those different IP addresses on a common set of switches across an entire campus or a business or something like that. So I can have different controllers talking through this FlowVisor that brokers the southbound traffic to switches based on their slice. That's this concept of what FlowVisor does. And it's been a research project, but something you could test yourself with open source software, but this is likely something that vendors will implement or have similar type of functionality to. So we might have different groups with different authorities using a common network infrastructure, but control them and keep them separated and separate their traffic appropriately based on our security policies, for example. Another popular SDN security use case is DDoS mitigation. Currently today, the techniques that are used for DDoS mitigation are access control lists, which have to be put on a network devices manually or scripted and pushed out to all the network edges to block the DDoS traffic from getting to the victim system. We use a NetFlow-based system to look at active flow traffic and analyze and identify flows, and then based on that control information, then go and make adjustments to network devices. We use remotely triggered black holes and things like that, but a lot of those systems end up taking the victim's system offline and completely disrupting, all traffic. The victim then has to change their IP address, update DNS, restore service, reestablish connectivity, and it's difficult to mitigate those. But with traditional network elements, and it requires, and many of those techniques require a human intervention to trigger something or go to a trigger router and enter a route to null zero that then gets propagated with BGP to all the other, BGP routers to then create the black hole, essentially. With SDN, we could do this in real time without human intervention. We could have a DDoS telemetry system monitor current traffic volumes, and when a DDoS condition occurs, send a traffic, identify the type of DDoS traffic, communicate with the controller that information, and let the controller push down rules and policies to all of the network elements to block that DDoS traffic. So have a DDoS detection system talk to the northbound API of a controller to then create and mitigate, create policy to block the DDoS traffic, and thus, but yet allow legitimate end user traffic to the target application and have it continue to operate. So mitigate the DDoS traffic without taking the victim system offline. We could use some more intelligence in the network to identify that malicious traffic and suspicious traffic towards the victim, but allow cleaned traffic, legitimate traffic, to continue to flow. There's many examples of this on the market. Radware's Defense Flow, their Defense for All Service, Open Daylight Helium has this capability built into it, A10 Networks, Thunder Threat Protection System, and there are others too. The way this works is you see normal traffic going from the end users here on the left over to the virtual machines on the right. We pass the traffic through this DDoS mitigation system, this Radware Defense Flow system. Based on and it can scrub out the bad traffic. It can then talk to the controller northbound and say, hey, I've identified this bad traffic. Let's push out to the network elements of the virtual switches and block this DDoS attack traffic. So Radware Defense Flow works with Cisco's Extensible Network Controller, Open Daylight, Big Switch, and NEC's programmable flow controllers as well. So many vendors here collaborating, working together to create these types of solutions. So another popular SDN security use case. I'm sure many of us we've all heard of NAC, Network Access Control, Network Admission Control, the ability to prevent unauthorized access to our networks from end user access, wired or wireless connections, or to quarantine end user desktops or devices that have malware on them or have become out of compliance, and then push them to an automated malware quarantine, remediation network to either get their, their antivirus patches updated or clean them or put them into a quarantine VLAN to keep them from infecting other hosts on the network. We've all had this idea that NAC systems could do this, but sometimes they're difficult to implement. But maybe we could use an SDN system to intervene, identify those hosts that might have malware on them, and then take action by pushing the Ethernet port and changing the behavior of the Ethernet port in the network element to isolate that user, or be watching traffic traversing the network for malicious behavior from the end user, and then based on signatures from the network elements identifying that the user is behaving badly, or maybe it's insider threat, or something is not right, then automatically quarantine that user without human intervention and then let someone go about remediating. Also, end nodes, we want to have network elements that are more intelligent than just traditional Ethernet switches that just put ports into VLANs. The IETF has this source address validation improvements working group that is taking some of the functionality in a DSL or a cable MSO infrastructure like a CMTS, cable modem termination system, and putting those functions about that service providers have used for many years to prevent subscriber-to-subscriber traffic, prevent subscribers from doing bad things to the network devices. These service provider broadband internet access systems watch and observe DHCP traffic to determine which MAC address has which IP address through DHCP allocated to it, and that should be the address that that system uses to source traffic from. If traffic starts being sourced from a different address, then we know that there's address spoofing taking place and that should be blocked. We have first op security for IPv6, of course, as well, integrated in our network devices to mitigate IPv6 neighbor discovery protocols. But we could take these functions and put them into a controller and then have the controller push out this information to network elements. So we could use Cisco's Cloud Threat Defense System to detect an issue, or use ICE and then set a security group tag in TrustSec to bad to containerize the traffic. You know, HP Van Sentinel has a security application. We could take Identity Services Engine with a network controller with a service abstraction layer to push whichever type of southbound protocol is required. You know, we can talk to an API on an ASA firewall. We can talk, you know, to different network elements from this control layer and have information, near real-time information about behavior of network access users, nodes, change how things are set up. So another possible use case that might be easier to implement, or more real-time, or allow some more functionality than traditional NAC systems that have been fairly restrictive. We could do monitoring. Many switches often lack hardware resources, CPU capability to do packet mirroring or do taps. Every group wants to have their own, you know, view into the network. The security team wants to look at certain kinds of traffic and send traffic to a web application firewall or to an intrusion prevention system. So network packet brokers have been popular, but they often can be very expensive. We want to be able to see bidirectional traffic. That's much better than, you know, aggregated NetFlow traffic. So some of these taps can be expensive. And so maybe we could use the SDN switches that are already in our infrastructure that use, you know, commodity ASICs and are very low cost, but then use an SDN control function to manage them. An example of this would be the Cisco Extensible Network Controller Monitor Manager app that uses the Cisco Nexus 3000 switches that are fairly economical to create a tap aggregation system. Big Switch, Big Tap Network, and others operate like this. So we have a control network, and based on, we can then take any port in the data center and tap it and span it and send it to an out-of-band network. So we could very easily build a packet broker monitoring system this way. Moving target defense is this concept of changing behavior of a network with this MTD6 function here between these two nodes. And with IPv6, because of the vastness of the IPv6 address space, we can change the source address of the devices on the left side, change the addresses on the right side rapidly, so the attacker in the middle that's eavesdropping, it looks to them as if there are hundreds and hundreds of systems over here talking to hundreds and hundreds of systems over here and confuse them. So kind of systems would change their IP address, send some portion of traffic, then change their address again, then change some traffic. And so systems are basically hopping around among IP addresses, or at least that's what it looks like to the eavesdropper. These systems are changing their addresses and then sending traffic. And so it confuses an attacker. They don't know which address to attack then at that point. So it's periodically hiding, changing characteristics of the victim, making it more difficult to attack. So this is done in kind of an application or an appliance. It's not done in the end host. We don't need this functionality in the end host, but we could use applications in a northbound API and a controller to adjust these network elements to then change this behavior and kind of create a defensive mechanism for networks based on hiding and moving targets. So if the target keeps moving around and hopping around, you can't see them. You know, you move around and you can't be attacked because the attacker doesn't know what your next IP address is going to be. So this is kind of this concept that these research students are doing at the University of Virginia Tech Security Laboratory. So these graduate students have created this concept and published papers on this subject, but it could be implemented in an SDN system. So, so kind of to summarize what we've talked about here, those were the 6 use cases that we talked about. So in summary, SDN, has the potential to provide, many new and interesting ways of handling traffic and securing systems, handling traffic, and then having that be controlled based on policies and not being, performed manually. It could be more adaptive, could be more flexible, could be easier to maintain, could give us greater agility and faster response time, could give us better visibility into what's happening, and visibility is key to being able to secure anything. SDN gives us this new way of thinking, and we need to be cognizant about SDN as this technology shift occurs in the IT industry, and think about, well, how could we leverage SDN to improve the security of our systems? But then also, as we move to implement SDN, we want to make sure it's secure right from the get-go. We want to anticipate what attackers could do, and we want to harden it against these security attacks and prevent that, from the onset. But SDN systems can provide these new innovative security applications that were not possible with traditional methods and network devices and security devices. And so hopefully today's presentation is giving you a new perspective on SDN and giving you some ideas on how it might be used to benefit your organization. I have some articles here, some resources that you can look to. I've written a few blogs on Network World, on Cisco.com, along the lines of what we talked about today. You could check out these articles, and there's many other resources now on SDN security. It's becoming quite a popular topic. So every day there's more articles written on it and give us ideas into what research is being done on the topic. But just like SDN is a rapidly evolving industry, SDN security is just as rapidly evolving. We just don't want to leave security as an afterthought to our deployment. We want to plan it right from the get-go. So what we've been doing in this SDN web seminar series is offering a free 3-hour, half-day SDN technology review for your company. So if your company is interested in hearing from our SDN experts at GTRI, we just ask that you bring together a group of teams, network, security, DevOps, other technology teams to the conversation to talk about how SDN systems may be used at your company, maybe how they might benefit your organization. And so by pulling together an interdisciplinary group, you can have a better conversation about how SDN could benefit your organization. So we could kind of review what SDN capabilities exist in what you already have, talk about what architecture might make sense for based on your business goals, review how automation or programmability could be used in the near term, and engage in conversation about what the long-term, deployment might be for SDN or IPv6 or security or anything like that. So with that, that's the conclusion of the presentation. We've got some time for some questions. So go ahead and put some questions into the chat window if you have them, and we can answer them. In the meantime, while people are entering in their questions, I'll just remind folks this is being recorded. You'll be able to watch the replay if you want to be reminded of something we talked about today, or share this with a colleague if they're interested. We are going to provide the electronic information about the PowerPoint for the presentation that was given today, so you could review that for your reference or to share with a colleague. Here's my contact information if you have questions after today. If you can't think of anything right now, but in 20 minutes from now you come up with a question, feel free to reach out to me and I'll be happy to answer it for you if I can. Okay, so here's a question I see. If I am a security administrator, do I have anything to worry about with the introduction of SDN? Should I be afraid that this will eliminate my job? That's a common question. I think we got that same question on the Intro to SDN web seminar. If you're a network engineer, are you concerned that SDN will eliminate jobs? I think it might if all you do is, as a security administrator, is add permit statements to firewall policies. If that's your only function in life, and you do it manually, you basically just respond to trouble tickets and add rules to firewalls, yeah, you might be in danger of being eliminated. But most, security administrators, wear multiple hats. They're very knowledgeable about current security threats and help their organizations, try and adapt to the changing threat landscape. And so you will use SDN systems as a tool to help you increase your efficiency, increase your productivity. So it's just another tool in your tool belt. It may save you time, may allow you to, improve what you do. And I think you'll naturally, learn about SDN and learn how to secure it, learn how to leverage these types of control automation techniques to improve what you do, and get you out of the day-to-day mundane activities and move you to being more aligned with the business and give you the time to create security solutions that you didn't have time to work on before because you were busy manually, adding in policies to devices, and now you would have software-defined security systems that would allow you to just observe and have greater visibility to a global sense of what's happening in your environment, and get away from having to do things manually or do things, based on you doing it. The network would be more automatic and automatically take action based on some policy you created, based on your experience and knowledge of security as a field. So I think you could still be relevant, and I think you would want to learn about SDN systems and how they could be a valuable tool to you to improve your productivity. Okay, here's another question. I hear about microsegmentation from several vendors. Can that really solve all my security problems? Microsegmentation, we talked about it briefly today's talk. Microsegmentation, just for those who may not know what that is this concept of taking a flat VLAN. Let's say there's many systems in a VLAN 100 in your data center. On VLAN 100, it's a /24 IPv4 address prefix on that LAN segment, and there are many different systems on that LAN. There's HR systems, there's marketing systems, there's finance systems, there's other types of file shares, email servers, all kinds of systems in this network, and they don't all necessarily need to have permissions to talk to each other. Or we may want to constrain HR systems only talking to the folks in the HR department. Now, microsegmentation would allow us to take those 4 or 5 HR systems in VLAN 100 and create a microsegment with just those 5 IP addresses, not sequentially, not based on an IP address mask, but create an enclave of them and isolate them from other devices on that LAN, kind of like what you've done in the past with private VLANs. Could we create a simple microsegment with just the HR systems? And then can we put a policy on there, an access list, some stateful policy that says, only HR users can reach the HR databases. So someone in the marketing department that might have gotten their laptop infected with malware couldn't communicate to the HR system directly, like may be the case today. Maybe you have an enterprise where any user can talk to any server in the data center. There is no filtering or segmentation. And you want to make sure that only HR users that have a legitimate need to be interacting with those HR applications do so. So microsegmentation can segment the network and then apply a policy to just the HR databases. It is possible, and microsegmentation is a feature of some SDN systems, but it's not a panacea. It still requires you to have some, identity-based security method to say, I know who the HR databases are, or HR users are, I know which applications are in use, I know which systems are the HR systems, and I know which IP addresses they have, and they may be physical or virtual machines in my data center, and I know where they're connected to the network, and I want to push that policy down. So it requires a lot of knowledge and some disciplined approach to make it useful. But generally, many vulnerabilities are at the application layer, and the microsegmentation isn't necessarily fixing the application vulnerabilities. Maybe that HR database has a web-based application that has a buffer overflow vulnerability in it that isn't repaired, yet the enterprise hasn't fixed it because they feel like, wow, this is an internal application, it's not publicly facing, so we haven't fixed that issue. Well, microsegmentation isn't going to fix that application vulnerability. It can help. Microsegmentation can be a piece of a security architecture that helps you create an orbital security model or a layered approach. It can be a component and a compensating control of a broader security architecture for your data center, but it can't automatically fix all types of security problems in your organization. So it can help, but it can't solve all your security problems. Okay, so those are the questions that we got and all we frankly have time for today. So I appreciate everyone's time. Again, if you have questions, you can send them to me offline. But this concludes our SDN web seminar for GTRI. I'm Scott Hogue. Again, thank you for attending.